introducing Dr. Yuping Huang from Stevens Institute of Technology.
Thank you, Monica. Hello, everybody. My name is Yuping Huang, and I'm an associate professor from Stevens Institute of Technology, and I'm very glad here to join this wonderful two-day conference and to report some of the quantum research that we are doing under the sponsorship of CERC. So the project is quantum photonic tasks for research, and our goal is really to see if we could create transformative quantum system engineering. So we hope to see what we can do with quantum. So here is the outline of my talk. So first, I would like to introduce a little bit about the quantum science and engineering. What is quantum? Why quantum now? And the different systems for quantum and why we are using optics, which is the emphasis of our sponsored research. And the second is the quantum photonics tasks for research, where I'm going to describe some of the cutting edge quantum research at Stevens and the quantum encrypted networking system as a part of our project, and the integrated quantum nanophotonics and application, the second part of our project, and third is to explore the transition of research into production. So in the third section, I would like to have some brainstorming on what's the next many of you why system engineering is critical for quantum development, which is a really heated global race right now, and how quantum technology will potentially transform system engineering, and what's the opportunities and challenges that we are having for the quantum system engineering. So which hopefully will be the topic over the next few years or next few decades. And finally, I would like to conclude and offer some of my own perspectives. So first, what is quantum? So it could take many days, but here I just would like to very briefly tell you a little bit my own understanding about quantum mechanics. I believe that it is most accurate theory towards the physical reality. And as much as we love Newton's law, as much as our world is built upon Newton's law, they are just approximation of quantum mechanics. And in fact, when I was a PhD student, I had a lot of fun deriving Newton's law from quantum mechanics. So quantum mechanics is really a very fundamental law of physics. So as you can read of news and see a lot of announcements at this very exciting time on quantum, I would like to remind you that actually quantum is not a new subject. In fact, we started to learn and utilize quantum from over 1 century ago. And quantum is also very counterintuitive. So there are many spooky actions around quantum. And here I would like to offer 3 examples. In the first example is the quantum superposition principle. In the classical world that we all are very familiar with, so you can, if you have a light bulb, you can either turn it on or off, okay? But it cannot be both on and off. But this has been fundamentally changed in quantum world, where you can actually have a light bulb, the single light bulb, both on and off at the same time. So in the second example, that In a classical world, if you wanted to synchronize two distinct light bulbs, you would like to, we definitely need some sort of physics connection. Okay, so you, for example, have to connect the two using a wire. So, and such connection must be time-like and local. Okay. On the other hand, quantum does not need any of those. Okay, so if you have two light bulbs that are synchronized, and then you send one to the Mars and leave the other on the Earth, surprisingly, the two will remain synchronized. So this is a big mystery of quantum mechanics, and people call that quantum entanglement. So such connection is non-local, and it can be realized through space-like connection, because we don't need any physical connection between them to make it happen. So in the third quantum oddness is that in the classical world, in principle, at least in principle, you can duplicate a light bulb and create an identical copy. But this is definitely not allowed in the quantum world. In the quantum world, it's not possible to create an arbitrary identical copy of an arbitrary unknown quantum state. So because of this very distinct features in quantum, actually people have been able to derive a lot of very powerful applications, and we are going to touch some in the next 30 minutes of this talk. So now quantum is very odd, and it's very interesting, but the big question is that why is quantum now? So we have not used or relied on quantum over the past century, right? We did not build the George Washington Bridge using any knowledge on quantum. Why now? Well, so there are many reasons that why we should really look into quantum now. So here I'm just going to offer some of my own understanding. So the first reason is that we need quantum to better understand the nature, our mother nature, and also ourselves. And in fact, there are a lot of evidence now that nature knows how to harvest quantum effects to make, for example, the photosynthetic process very efficient. And there are some very surprising research finding that our human bodies are already utilizing quantum effects to enhance our sensing capabilities. So have you ever wondered why our noses are so sensitive to a particle maybe in over 1 million? So have you ever wondered why our eyes are so good and we can see very silent features and even in darkness? So those questions actually are being answered from the theory of quantum mechanics, and maybe one day people will find that our own consciousness has something to do with quantum. I don't know, could be. After all, so the quantum is the most accurate, and I believe is the most fundamental theory of the physical world that we are living in. And the second answer is that it is important to advance our technology. So although we are very proud of our technology state as of now, there are a lot of things that we could not have imagined 20 years ago, and now we're using that. But there are more and more problems that we're facing as well. We are facing the big data crisis, the cyber security problem, we can only assume, or we can only hope that our internet is secure. And we are challenged by the renewable energy. And as a scientist, I always feel that we must do more dealing with cancer and now the viruses, right? And so what we have to keep in mind is that we are living in a quantum world, and there are many problems that can only be solved by using the quantum tools. So another more motivation is the breakdown of the Moore's law. Over the past decades, our society has been on the wheels of the Moore's law, where the number of transistors on a single full footprint chip fortunately, we are going to see the end of it, because we simply reduce the size and the length of the transistors to only a few atoms now. So we are already running into the quantum regime, and the answer would be that we have to build quantum computers. I think these days you must have heard a lot of news on both the government and the big businesses running on the race of building the quantum computers to demonstrate the quantum supremacy. So, because this is the next step for computers. So right now, so there are several candidates to build the quantum systems, and here we show some images of trapped neutral atoms, and here this is trapped ions and superconducting qubits, and here is optics. So at Stevens, especially in my lab, so we focus on building quantum systems with photons. So what is photon? A photon is a fundamental particle of light. So a solid. Okay, so photons do not have rest mass. It constantly travel, and a photon has energy of 10 to the negative 19 joule. So this is really teeny tiny energy. You can imagine that if you have a light bulb, if you plug in, it actually, if you convert its illumination to how many photons per second. So this is enormous. Okay. And what's really nice with photons is that they are free, they are fast, they travel at the speed of light, they are very robust against decoherence and loss, which allow them to be transported over a long distance without losing the quantum properties. They have extreme bandwidth and multiplexing capabilities. So imagine that we can use a single piece of fiber to support terabytes communication. This is indeed enormous. And over the years, we have developed so many tools to work with photons. So they are easy to operate, and distribute. Indeed, it is those very nice free properties of photons invited us to really to build quantum systems around photons. So there are lots of potentials for the photonic quantum systems in areas of biology, metrology, sensing, computing, internet, medical, intelligence, imaging, crypto, and big data. So the potential is really, really infinite. And at Stevens, we are very proud of our highly interdisciplinary quantum research, where we built our core around the innovative quantum engineering. Stevens has been a leading force in the engineering research and education for the past over 1 century. And now we are transforming this into the quantum engineering. So using photons, we are looking at some nicely engineered systems for the impact in computing, quantum AI, sensing and measurement, biochemistry, control and robotics, and quantum communications with applications in many different areas where we can potentially make huge contribution. So a little bit about my lab. So my lab is called Quest, Laboratory for Quantum Enhanced Systems and Technology, where I have 30 plus researchers. With currently I have 21 PhD students, 2 postdocs. Actually, now it's 3 now, and I have a lot of masters and undergraduate students, and I have 6 lab rooms and have over 4 million state-of-the-art equipment, especially designed for the quantum photonics research. I've been very fortunate to receive the federal support to carry out a lot of research around the quantum photonic systems. And here in the lab, so we not only have students, PhD students in physics, but we have students from computer science, electrical, and computer engineering, and students from mechanical engineering. So those really allow us to boost our expertise in not just quantum research itself, but in nanophotonics, quantum optics, FPGA electronics, and software development. So our secret ingredients for our research is really that we start with quantum empowered optical technology, right? And we embed them in the integrated photonics to create robust systems of commercial and defense values. Okay, now I'm going to jump to the second part of my talk. So the first task in the sponsored research is to build quantum encrypt networking systems. So with the goal of developing design patterns, operation strategies and protocols, and develop prototypes for assessing hybrid quantum communication systems, and the abilities to provide robust and unconditional secured communications in a challenged mission environment. So here, our goal here is not on the quantum research itself. It is on how to transition the quantum physics, the quantum technology that we have already built in the past, how to transition that into systems, and how to maximize their impact, how to realize them with reasonable cost, and how to make sure that they are reliable when operating in a challenged mission. Okay, so this research actually leverages our own Stevens hybrid quantum campus, where we have already built a quantum networking system across the Stevens campus. The three dots that you can see on the Stevens map is where the three quantum nodes are, and we are connecting the Bersha building at Stevens with the library through a piece of telecommunication fiber, and we are connecting the Bersha quantum node with the Babel quantum node through a three-space link. And for our user experience, we also built the quantum corner and in the library, and it ran for about half a year. Unfortunately, due to the pandemic, we had to shut it down. So I hope that we will be able to get online, hopefully in a few months. So under this sponsored research, we also built the programmable quantum random numbers, and so those are very important for a lot of encryption and also for the big data simulation. And we are building very unique quantum device and this system that fully run on a 12-volt power, okay, DC power, and we can the probability distribution and the statistical property of the random numbers that we create, and the whole system is scalable. And we also make it modular. The numbers, and all those are just a starting point, I should say that, so they could be followed by a lot of very interesting applications. So in another task, we focus on building the quantum integrated system using lithium niobate thin film and utilizing the latest nanophotonic fabrication and experimental progress. So the goal here is to further development and transfer of advanced quantum nanophotonic technology that we have already developed and at Stevens, and we hope to transfer that to meet the needs of CCDC-AC and with applications in linear optics, nonlinear optics, quantum random number generator, and where we are going to utilize this chip device to significantly reduce the footprint and the swap of it in quantum LiDAR. So why we're choosing this particular material as our platform? Because it has very nice properties that are very important for the build of the quantum systems. It has very large optical nonlinearity, very wide transparency window that can pass close to UV and mid-IR light. So this is of a large span of bandwidth. And it has very large electro-optical effect, very little Raman noise, so that we can make sure that our quantum processes remain pure, little to photon absorption and little free carrier effects, and many other very nice features that could definitely benefit our engineering efforts. And with that, actually, we are developing many different applications and systems. And unfortunately, I will not have time to go through each of them. So in another task, we explore the transition of the research into production. Here, we very specifically use the photonic LiDAR system as a example. So it is a very unique LiDAR system that has enormous advantage over existing systems by being able to see through impossible. So even if you have very thick fog and cloud, whether it rains and whether it snows, whether there's smoke, and our LiDAR can see through those obscurants. And in addition, so we can see very, very far, and our system will allow us to achieve millimeter range and resolution of tens of kilometers. And another very interesting feature is that our LiDAR allow us to see project without being seen. You don't want it to shine a strong laser beam on the target you want to measure. Okay, so you wanted to do that using very, very weak laser power. So that's what we can accomplish. So actually, we invented this technology back in 2015, and then we were able to verify that in an experiment in 2017, and where we show very good agreement with the measurement result and our theory. So, and then between 2018 and 2019, actually, we were able to put together device which actually include a lot of optics and electronic hardware, and we have to develop our own FPGA electronics. And we also, I'm very proud that my students, they also built the software and applied the error correction. All did this by ourselves and did some scenario studies, and this picture shows our system. And now for that effort, okay, so our goal is to explore the transition of the research into production. What we have been able to do is that we have been able to put a lots of optic elements on a single chip, as you can see here. Okay, so we're utilizing this integrated chip technology to explore a very wide system engineering trade space, and that also allow us to put the entire system in a portable, compact box that people can use and can provide very reliable performance. And here is the system that we have built. As you can see that indeed, so now we have been able to put everything in a box, and the box is still a little bit larger than what I hope, but I cannot complain too much as my students put a lot of effort in this. It's much harder to build a system from the scratch than purchasing one. So this is a system entirely owned and invented by our Stevens team, and which consists of wonderful cutting-edge research and development in optics, nanophotonics, FPGA, electronics, and we have also developed our own user interface and did some field testing to make sure that it works properly. So I think this is our first portable quantum LiDAR system. Okay, and We certainly have a lot of more work to do here, but believe that from what we observed, can already start to make huge impact in the field. Indeed, so those are just a part of what we do at Stevens. In fact, our opportunity can spread over a whole horizon. So, for example, by modifying the system, we can develop a quantum hearing system where imagine that you can hear very weak sound from miles by just shining a very weak laser beam. Okay, quantum saying if you go into a new environment, you wanted to know the nature of it. You wanted to get a very quick assessment. Okay, so then you don't want to use a digital camera to take a picture of everything because then it will take enormous amount of time for you to process information. How about what if we can have a camera can give you the picture that you are interested in? It's so smart. Okay, we're not talking about any post-processing or machine learning or AI. We're talking about the pre-processing. So the image processing, the data analysis are done before the image is taken. Okay, and also we are interested in developing the quantum smelling. So imagine that you can detect a trace level chemical miles away. And quantum thinking, we hope to use the enormous computation capability to boost our machine learning and AI capability. All right, and quantum ID. So imagine that you can create a credit card secured by quantum physics that nobody can ever duplicate. It's yours. It's safe. And there are indeed a lot of other opportunities that we're ready to push at Stevens. Unfortunately, I don't have time to chat too much into that, but please just let me get to my own thoughts about the notion of quantum system engineering. So, in the one hand, system engineering is very critical for the quantum next steps. As I said at the beginning of the talk, there is very intense global race on developing quantum technology. Okay, so in US, we are facing enormous challenge from many countries all over the world. How we can win? A key part could be played by system engineering. We have already seen a lot of exciting processes in individual development of quantum device, quantum technology. Okay, so a lot of proofs of concept and individual devices, detectors, and I think we are leading in many of those individual ingredients. On the other hand, we have immense challenges that we needed to address before we can take our quantum devices, quantum systems into the field and make impact. For example, quantum information carriers are fragile and the quantum systems are complex. There's a big gap between quantum and the classical system interface. Okay, usually quantum physicists don't talk with engineers, so then that's a big issue, right? And also, we still have to find good ways for us to better interface quantum and classical systems. And there's also a strong gap. There's a pretty big gap in the workforce development. So I think in these areas, systems engineering can play an important role by lending its very critical strategy and tools. Okay, so to especially with the goal of creating impact in the defense sector. On the other hand, so quantum technology can transform system engineering. For example, here is some of our latest results actually. So we utilize a nonlinear optical ISM machine that allow us to optimize a system that correspond to having 1 million free parameters with interaction. Okay, so typically, typical simulation systems can only capture the interaction between two bodies, which people call two-body interaction. But we know that in a realistic system, the interaction is always much more sophisticated, and we have to consider high order effects. And here we, for the first time, demonstrate that yes, indeed, we can simulate the four-body interaction, so which allow us to construct extremely complex network. And with that, I think we should be able to simulate prediction, predict and analyze very complex systems like never been able to in the past. So in another opportunity, so quantum offers us a pathway to have very trusted, very reliable authentication and command over even untrusted network parties. Okay, in fact, we don't have to trust the other party to ensure the authentication. Okay, so I think this is only possible using quantum ways, and here we have done some very preliminary work, and we find that indeed, so this is possible. And in another system also we put together in my lab. So we have built a hybrid reservoir computer. As you can see here, we have been able to put everything in a box. So this is electronics and optics. And with that, actually, we have been able to very precisely and accurately predict 2,000 future steps in a chaotic time series. So I don't think this has ever been done in the past. And what I have shown you is just some potentials. Okay, so what we can quickly work on and to push our research into product, into impactful technology by using the advanced system engineering approaches, and with hopefully help from wonderful experts in the system engineering. Okay, so but there's really a much broader toolbox that we can play with and we can harvest on. So that naturally leads to my thought: are we really looking at the dawn of quantum system engineering? We can use system engineering to help our agenda of the quantum enterprise. And in the meanwhile, we can already leverage very unique and powerful capabilities allowed by quantum devices, quantum technology to perform system engineering research at an unprecedented level. So this is really a very exciting front that I hope maybe be able to collaborate with many of you and to see what we can do as a team. Okay, so I think that would be the end of my talk. And here I just wanted to give you a development trajectory in my lab. So in 2007, okay, so when we did a experiment, we had to use a full load of optical tables. So those are the 4 foot by 8 foot optical table, and we have to put a lot of optics there. In 2018, we have to be able to put all of those optics in a small box of the size of a cell phone. Now in 2020, we have been able to further reduce the size, okay, to a single photonic chip, non-photonic chip, that is only a fraction of the size of a penny. So I think we are really ready to jump into a very exciting field where we can use our integrated photonics and put that into systems and see what can happen. And I think my time is running up. Thank you so much for coming to my talk, and I hope to connect with you either in the Q&A session, or please feel free to send me an email or type your questions. Thank you.